Let's try an example to check for the stress limit of a pre-stressed beam. In these questions, a cross-section of the bridge deck is given. The bridge deck have a width of 5.5 meter. It is used to sustain the load of 5 kN per meter square GK and 10 kN per meter square QK. The bridge deck is supported by 6 units of pre-stressed beam. The pre-stressed beam is in the form of T shape and the dimensions are given here. The beam is simply supported over a span of 12 meters. The concrete used is 60 Newton per mm square at surface, and at transfer, the concrete strength is expected to reach 40 Newton per mm square. There is a tendon at the prestressing load of 1860 kN. There is no eccentricity at the end support, and the eccentricity is at max when it is at the midspan. The eccentricity at the midspan is given in the diagram here. The short-term losses and long-term losses are given as 7% and 12% respectively. The concrete unit load is 25 kN per meter cube. Ignore the weight of the concrete diaphragm. You are asked to draw the stress diagram and construct the 4 equations to calculate the stress at the pre-stressed beam, at the midspan, and at the support. Next, you are asked to calculate the stresses at the transfer and at the service date. Then you are asked to check for the limit, whether it is exceeded or not. And then from the result, you are asked to describe the implications when the eccentricity is increased. And also describe the changes in terms of the 4 equations if an additional tendon is provided. You may pause the video for a while for you to work out the solution. To solve these questions, first you need to determine the UDL acting on each of the beam. It is given that 6 units of the pre-stressed beam is used to support a bridge deck of 5.5 meter. Therefore, the ratio can be used. The service load will be GK plus QK multiply 5.5 meter divided by 6 units of the pre-stressed beam. The UDL is found to be 13.75 kN per meter. The questions asks us to construct the stress plot diagram for the midspan and the support. For the midspan of the member, there will be axial stress, bending stress, and also due to the eccentricity. With that, the top fiber stress is calculated by the axial stress plus bending minus eccentricity. The bottom fiber stress, it will be the axial minus bending plus eccentricity. That gives us these 2 equations for the midspan. Next, at the support here, there is no eccentricity and the moment is equals to 0. In this case, the contributions of bending and eccentricity is ignored. With that, the stresses at the support is purely governed by the axial stress. With that, two equations of stresses is obtained at the support. The top and bottom stress will be the same. Next, the values are substituted into the spreadsheet for us to do the computations. We need to determine the geometrical property of the member. As the member only consists of the T-shapes, that means we can simply ignore this from the spreadsheet. The area of each element is calculated. The respective centroid of the elements is calculated. This column is calculated by multiplying the A with the Y. Sum up the A and sum up the AY. The centroid of the member is calculated by dividing this with this in order to obtain this. Next, we determine the centroid from the top surface of the beam. It is obtained by minusing the total height with the Y bottom. You get Y top. Next, we need to determine the moment of inertia of the sections as given in these equations. The second moment of inertia of individual element is calculated by using BH power 3 divided by 12. The dy is obtained by minusing the y with the centroid of the member. This is obtained by minusing this with the centroid of the member. The A dy square is obtained by multiplying the A and dy square. This column is obtained by this plus this. The summation of this, it will be equals to the second moment of inertia. The section modulus is calculated by the I divided by the centroid. For the Z top, the I is divided by the Y top. For the Z bottom, the I is divided with the Y bottom. Next, we check for the stress limit. The compressive resistance limit is given by 60% of the concrete strength at the stage. The concrete strength at the transfer stage is used here, and the concrete strength at the service stage is used here. This gives a slightly smaller stress limit for the transfer stage. At the transfer stage, the flexural crack is allowed, while at the service stage, flexural crack is not allowed. When the flexural crack is allowed, FCTM is calculated. It can be referred from Eurocode 2, Table 3.1. When flexural crack is not allowed at the service state, the tension stress limit it will be considered as 0. The self-weight of the member is calculated by multiplying the area of the member with the unit load of the concrete. As for the service load, it will be the summations of the self-weight plus the GK and QK. With that, you are able to calculate the moment of the member. The M-mean is calculated by substituting this into the equations of WL squared by 8. As for the M-max, is calculated from the UDL at the service state. Next, you refer back to the equations at the stress plot diagram. Substitute the relevant equations into this. The stresses are calculated as given here. The alpha is meant for the transfer and the beta is for the service state. The M-mean is meant for transfer stage. M-max is for the service stage. The Z top and Z bottom referring to the top beam and bottom beam. These stresses are to be checked against the stress limit which we have calculated earlier. It is found that all the stress are within the limit and the member is considered acceptable. Next, we need to answer the questions on describing the implications to the prestressed beam if the eccentricity is increased. By looking at the equations as you have developed from the stress plot diagram here, there is no eccentricity in the equations of the support. Therefore, increasing the eccentricity will impose no effect to the support. The eccentricity will affect the stresses at the midspan of the beam. Based on the positive and negative value here, you will know that increasing the eccentricity will reduce the top fiber stress at the midspan and increase the bottom fiber stress at the support. The question proceeds with asking us to describe the changes in terms of 4 equations if there is an additional tendon provided. When there is an additional tendon, there will be P1 and P2 and E1 and E2 in the equations. P1 and E1 is due to the first tendon and P2 and E2 will be due to the second tendon. And then go back to the equations which we developed earlier in the stress plot diagram. The new equations for the support will be the summations of P1 and P2. As the prestressing load and eccentricity is not clearly stated in the equations, we can quantify them separately. That means you duplicate the effect of the eccentricity for the second tendon. This gives you a new equations look something like this. Or you may choose to combine the equations where there will be E3. And the E3 is the new eccentricity which is calculated based on the centroid of the two tendons. These two sets of equations should give you the similar results. The equations for the supports are the same. And then, based on the equations that we have developed, we are able to observe the effects on the stress in the beam. When there is an additional tendon, that means it will be an increase of the prestressing load. The increase of the prestressing load here will increase the stresses at the support. As for the midspan, It increases the stresses in the support, but it may reduce the stresses due to the eccentricity. We will expect an increase of the bottom steel stress in the beam due to the additional tendon, but it is difficult for us to judge whether the stress going to be increased at the top fiber of the tendon. The main reason is it is very dependent on the E and the P. The top fiber stress will increase when this is greater than this, but it will decrease when this is less than this.